Minimum cost to cut a stick of length n, right? So we are given an array, we have to perform these cuts on the stick. The problem is that we have to find an optimal sequence of cutting them. There is a cost associated with each cut, and it actually varies dynamically. It's not simple mapping, like if you want to cut at 2 the cost is 8, if you want to cut at 4 the cost is 7. It is not associated like this. It changes on the past decisions that we choose to cut. So basically the cost at a particular cut is the length of the stick at this moment. So you can see here, if we, this is our entire stick of length 10, if we choose to first cut at 4, here the length of the stick is 10, so the cost at this cut is 10. Then it gets divided here, there is only one option here, we have to choose to cut at 2. The cost associated with this is 4 minus 0, 4, and here we choose to cut at 7, the cost associated is 6, so the summation is 20. But suppose if you have chosen another sequence of cutting them, like 2, then 4, and then 7. Suppose you cut at 2 first. So you make a cut here, the cost is 10. Then you cut at 4. So the cost here is 10 minus 2. This entire segment is different already, right? It has already become a leaf node. So the cost here is 10 minus 2, which is 8. That is added to 10. Then we can make a cut at 7. The cost would be 10 minus 4. So that is 6. So 10, 8, 6, which becomes 24, which is greater than our 20 optimal answer. So we have to determine the optimal sequence. So you can relate this question to MCM problem, where was also cost associated with every partition, and we are solving it with the same method, like we are initializing two pointers I and j, and we're trying all possible cuts, like if when we cut we form two sub arrays, right, to another recursive calls to solve for left part, that is I to k, and to solve for right part, that is k to j, right, k to j, whatever. So the solution here is that first we will add 0 and n to our cuts array for the sake of simplicity. So our array will become 0, 2, 4, 7, 10. Then we will sort this. You can see in the second test case, the inputs are not given as sorted, and we are maintaining kind of ranges of elements, right? So we have to make sure that it is sorted. Then we can initialize a DP vector. The size of this would be, we are maintaining two states, I and j, two indices. So it would be a 2D vector, and also the size would be n square. Now you have to make sure you choose this n after adding these 0 and 10, not the previous n, otherwise it will overflow. The fourth is, we have to identify the termination case, that is j minus I less than equal to 1. Suppose the I, right, I value is at 0 and our j is at 2. So j minus I, it is not 2 minus 0, they are indices. So j is at 1. 1 index value minus 0 index value, that is 1. So that is our base case, because if we have a stick of 0 to 2, we cannot partition it further, right? 0 to 2 itself is a leaf node, as you can see here. So this is our termination condition, and we will try all possible cut sequences, right? So let's see the loop. We will start from I plus 1 and we will go up to j. So basically for I is equals to 0 and j is equals to 4, we will only go for these three values. We can perform a cut at 2, which partitions our array into this 0 to 2 and 2 to 10, right? We can perform to cut at 4, which partitions our array to 0 to 4 and 4 to 10. We can choose to partition at 7. We can't partition at 10. Why? because it will lead to 0 to 10 itself. One segment would be 0 to 10 itself, right? We are not reducing anything. This is not actually a leaf node. This is a single piece of stick, right? And we don't need that. We need at least a range. You can see every leaf node are ranges. 7 to 8 is a leaf, 4 to 7 is a leaf, 2 to 4 is a leaf, right? There is no single just 10 element in the right leaf node. So for I and j, we can only partition for the indices that are in between them. Now for partitioning, the left segment will be called I to k, as I said, and k to j the right segment. The cost associated with current partition is cuts of j minus cuts of I. Suppose the I and j are 0 and 4, so the cuts of j is 10, 10 minus 0, so the cost would be 10. If you want to visualize the recursive stack space here, you can see for 0 to 4, first we'll call for solving 0 to 4. We can perform a cut at 1 here, we can perform a cut at 2 here, and we can perform a cut at 3 here. So suppose we go into this optimal sequence, just directly see how this works. So suppose we are at cut k is equals to 2. So we can solve for 0 to 2 and we can solve for 2 to 4. So for 0 to 2, this itself, these are indices, right? These are not 0, 2, 4. These are not cuts values. So 0 to 2, which means we have a sub array of 0 to 4. And for 2 to 6, we have 4, 7, and 10. Right? So for 0 to 2, this one, the I here is 0 and j is 4 for this. Solve 0 to recursive call. So we can only perform at this index, that is 1. So at k is equals to 1, if we perform to cut it here, the cost is for 0, 1, it is 0 because it is a termination case. The cost at 1, 2 is again 0 because it is also a termination case. The cost of cutting here is 4 minus 0, which is 4. That is why here it is 4 written, right? Then for the another 0 to 2, right, this is the right partition, that is 2 to 4. So for 2 to 4, we can perform to cut at 7 only, right? So similarly, the cost here would be 10 minus 4. Here it is directly written, right? 6. So 4 plus 6, and we are maintaining the cost of this 10 comes from adding this value, cuts of j minus cuts of I, right? For 0 to 4, right, we have to add the cost, and we added for 0 to 2 then, and we added for 2 to 4. So 10 plus 4 plus 6, which becomes 20. So this is how it is working. If you want to see the code, here you can see we have added 0 and n to our array, then we have sorted it. Then m becomes the new size, right? You don't pick this n, we have to, and this n is just the length of the string. Don't even pick cuts dot size. You can pick cuts dot size. Okay, sorry. So this is our dp vector, 2D dp vector, initialized with -1, right? Representing the state is not calculated yet. We are starting from 0, m minus 1, because it is index, right? We are going up to a valid index only, m minus 1. So this is our base case that I discussed already. If the value is already calculated in our table, return from that only. This is our int max variable. This is the cost, right? So we have to pick max value. I plus 1 to j, we're finding the minimum of answer, and we can partition it I to k, then we can solve it further for k to j, and this is the cost of current partitioning, and we are just returning, right?